Hello and welcome to your favorite Shri Devi classes YouTube channel where we inculcate interest and confidence in science and engineering subjects. Today in our playlist of class 12th physics in subject electrostatics, we first learn the Gauss Law which relate electric flux calculation to source charge configuration as well as with electric field intensity, and we will study some application of Gauss Law and will try to explain almost all question patterns based on application of Gauss Law. Let's start. Counting of electric force lines is known as electric flux, and electric flux crossing per unit normal area is called as flux density or strength of electric field. So if A area is placed normal to electric force lines and total amount of flux psi is passing through it, then the ratio of flux and normal area is known as flux density or is strength of electric field. And if the same area is tilted by an angle theta, then flux passing through this new tilted position shown by this green highlight get reduced to a new figure psi dash, and now flux per unit normal area, that is A dash or A cos theta. This angle is theta, this projected normal area is now A cos theta. A cos theta is reduced by the same amount as flux has reduced, and we found that in similar electric force lines distribution, density of force lines or the strength of electric field is same whether area is placed normal or with an angle theta. So when an area is placed normal to force lines or area vector and electric field intensity vector are in the same direction, then amount of flux passing through that normal area is given by product of electric field intensity and area. And if area makes an angle theta from normal or area vector normal to the surface makes an angle theta with electric field intensity, then flux passing through that tilted area is the same as passes through normal area A cos theta, and flux passing through an area which makes an angle theta from normal to electric force lines is given by EA cos theta relation, or it could be written as dot product of E vector and A vector, where area vector is directed normal to the surface and theta is angle between E vector and area vector. Gauss Law relate total amount of flux crossing a closed surface and amount of charge enclosed by the surface. Here this positive Q charge produce outward electric field as shown by arrows, and on the surface a small dA area making an angle theta with E vector have small amount of flux E dot dA, and total flux can be obtained by closed surface integration. And as per Gauss Law, total flux coming out of any closed surface or closed surface integration of surface electric field intensity over the entire surface is equal to enclosed charge divided by permittivity of media. If surface enclosed more than one charge, then as per Gauss Law, the net or total flux across this closed surface is equal to the ratio of total enclosed charge, that is Q1 plus Q2 minus Q3, and permittivity of the media. So we can say total flux coming from any closed surface is closed surface integration of surface electric field intensity and is equal to ratio of enclosed charge and medium permittivity. Here all external charge, say Q4, also produce electric field contribution over the surface of this study, but the net flux contributed over this surface is only by internal charges, as external charge produce equal and opposite incoming and outgoing flux through this surface. So flux across any closed surface depends only on total amount of internal charges and is equal to total internal charges divided by permittivity of medium. We have to find out net flux across these four closed surfaces A, B, C and D using Gauss Law. Let's first consider this blue spherical surface A, which enclose three charges plus 2 microcoulomb, minus 3 microcoulomb and minus 1 microcoulomb. As per Gauss Law, total flux across this closed surface is equal to total enclosed charge divided by permittivity of air, and sum of these three charges plus 2 microcoulomb, minus 3 microcoulomb and minus 1 microcoulomb is minus 2 microcoulomb, and enclosed charge divided by permittivity represent a negative flux across this spherical surface, and negative flux means net flux across this spherical boundary A is incoming flux. Now consider this black irregular closed surface B, which enclose three charges plus 4 microcoulomb, plus 2 microcoulomb and minus 3 microcoulomb, and as per Gauss Law, total flux across this closed surface B is equal to total enclosed charge divided by permittivity, and enclosed charge is 4 microcoulomb, minus 3 microcoulomb and plus 2 microcoulomb, and the sum is plus 3 3 microcoulomb, and this enclosed charge divided by permittivity is net flux, which is positive or outgoing from this closed surface B. Now consider this brown cubic surface C. In this closed surface, the total enclosed charge minus 3 microcoulomb and plus 3 microcoulomb are equal magnitude and opposite polarity. Such charge configuration is also known as dipole, and this dipole got net charge 0. So the total amount of enclosed charge is 0. So net flux across this C cube would be 0. In the end, when we consider this black cube D, then it encloses all 5 charges of plus 4 microcoulomb, minus 3 microcoulomb, plus 2 microcoulomb, plus 3 microcoulomb, and minus 1 microcoulomb, and sum of all charges in this cube is 5 microcoulomb, and enclosed charge divided by permittivity of air becomes the total outgoing flux, which is positive or outgoing in nature. If a charge plus q is placed at the center of this cube, then we have to find out total flux across this cube and flux from any one face of this cube. This cube got 6 faces. So as per Gauss law, flux from cube is equal to enclosed charge q upon medium permittivity, and this central position is symmetrical with respect to all 6 faces. So this total charge symmetrically divide equally across each face. So one face got 1/6 of total flux or q upon 6 epsilon 0 flux. If this charge is not placed at symmetrical center position but some eccentric position inside cube, then total amount of flux will remain same as q upon epsilon, but we can't solve this problem flux across any face of a cube. If this charge is not placed at the center but little eccentric, as in this cube having size 5 by 5 by 5, this charge is placed from this bottom face at the center height of 3 meter, then we can say that if we construct a face of 6 by 6 size and form a cube of 6 into 6 into 6 meter dimension, then for this charge total amount of flux that by that 6 by 6 by 6 cube is q upon epsilon, and one face of that cube would have this much amount of flux. As 6 by 6 size got q upon 6 epsilon 0 flux, so this 5 by 5 surface area would have flux less than q upon 6 epsilon 0. A charge q is placed on the surface of this brown closed body. So this charge is neither outside of enclosed surface and nor it is inside the closed surface. If it was outside of this closed surface, we would have said that total amount of flux by that external charge across this closed surface is 0, and if it is inside the surface, then we would have said that total amount of flux across this closed surface is q upon epsilon. But here this charge is neither outside nor inside, just on the surface. So in such condition, to apply Gauss law, just imagine another identical closed surface and put that on the top of it. Now this charge is in between these two surfaces, then the total amount of outgoing flux through these two closed surfaces is q upon epsilon. Since these two surfaces are just symmetrical with respect to this charge, then flux across any one surface would become half of this total q upon 2 epsilon. So when charge is on one of the face of a cube, we can say total amount of flux contributed by that charge over this closed surface is q upon 2 epsilon. When such charge is placed on one of the side of cube, as on this brown cube, at one side we have placed a q charge. Now this q charge is neither inside nor outside, and we have to find out total amount of flux across this brown cube. So let's put 3 more cubes such that this charge become inside all 4 cube, and since this charge position is symmetrical with respect to all 4 cubes, so total outgoing flux across all 4 cube is q upon epsilon, and flux across any one cube would be 1/4 of total q upon 4 epsilon. When charge is placed at one of the corner of cube, as here this q charge is placed at one corner of this brown cube, then even when we consider 4 cube, this charge is neither inside these 4 cube nor it is outside. But if we place 4 more cube in front of these cubes, then we found that this q charge is just in mid of these 8 cubes. So total flux across these 8 cube surfaces is q upon epsilon, and flux from one cube would become 1/8 of total q upon 8 epsilon. So when charge is placed at one corner of a cube, the total amount of flux across this cube is q upon 8 epsilon. And now if we analyze this position of charge, then on these 3 shaded faces, E vector and area vector are normal to each other. So net flux across these surfaces would be 0, but the remaining 3 surfaces, this covered by dark black lines, this bottom bottom surface and this front surface are identically placed with respect to this q charge, and total flux across this cube is q upon 8 epsilon, and three faces equally share that total flux. So flux from one face would become q upon 24 epsilon. In Earth atmosphere, a non-uniform electric field is directed in vertical downward direction, and at 300 meter altitude its magnitude is 60 volt per meter, and from surface at altitude 200 meter its magnitude is 100 volt per meter. Now in this atmosphere a 100 by 100 by 100 dimension cube was placed, and we have to find out total amount of charge enclosed in this cube. So it is clear that this variation in electric field magnitude is due to presence of charge inside this cube, and since electric field is directed vertically downward, so only on this top shaded face A and this bottom shaded face B there is flux crossing, and the remaining four faces got E vector and area vector mutually perpendicular and no flux across those faces. Now at face A, E vector is normal to the surface, so total amount of flux is multiplication of electric field intensity and area of face. Area is 100 by 100 meter square. Electric field is 60 volt per meter. So total amount of flux in volt into meter unit is 6 into 10 raised to 5 at face A, incoming or negative. Similarly at face B, where electric field strength has increased to 100 volt per meter, the total amount of flux would become positive 10 into 10 raised to 5 voltmeter outgoing nature. So the net flux across this cube is net outgoing flux minus net incoming flux, and it is net outgoing flux 4 into 10 to 5 volt into meter, and as per Gauss law it is clearly indicate that this 4 into 10 to 5 is enclosed charge upon medium permittivity, or enclosed charge is net flux multiplied by medium permittivity, and permittivity of air is 8.854 into 10 to the minus 12 farad per meter, and enclosed charge is 4 into 10 to the 5 voltmeter. So enclosed charge would become 3.54 microcoulomb. We hope this informative learning video has increased your conceptual clarity and confidence about application of Gauss's law, and now you can handle all sort of examination questions which require understanding of Gauss law. Our other learning video of the same playlist will enhance your subject competency and scoring ability. If you feel these learning video valuable, do share it with your friends, and to get more from Sridevi Classes YouTube channel in terms of study material and online classes support, do join our YouTube channel membership. Thank you very much.